Okay, in part 1 of 4.3, we wrapped up with talking about the intermediate value theorem and kind of describe what it was, but I'd like to do a real quick example before we move on to the next part of section 4.3, which would be more about finding zeros. Okay, I've already got it written down here. Intermediate value theorem, remember, was a theorem that states if you have a polynomial function and you look at an interval, so you're looking at the endpoints of the interval, if the sign is different, so if the function is positive at one end and negative at the other end, for example, that means you had to have moved across the x-axis, which means there would be a zero there. So let's see how it works. So we have the function g of x, and there it is. And the question is, does it have a root in this interval? In other words, if I knew what the graph was, and I don't, but I could graph it, at -3 and -2, this interval, the question is, does the graph cross the x-axis in there? Well, when we put g equals -3 in, we came up with 42, so we're way up here somewhere. It's positive. At g equals -2, we got -7, so the thing goes at -2, we're down here somewhere. So the only way to get from here to here is you got to cross the x-axis to get there. So again, the intermediate value theorem said if the signs are different between two inputs, -3 and -2 in this case, then yes, you have at least one root. And that's what we have here, and that's how you answer a question like this. Just plug in. Now, it doesn't tell you a whole lot, and I think we talked about this before. Quickly, if I have something like that, and I tested this interval here, it's negative in both cases, so there's no sign change. So the intermediate value theorem can't predict anything. However, in this case, you can see there's two roots, but we just don't know that from the intermediate value theorem. Also, let's go from here to, say, this one. There is a sign change, so the only thing we know is there's at least one root, and maybe only one. But in this case, 1, 2, we actually have 3 roots. So it gives you a little bit of information, not too much. And then finally, the other thing is you have no idea what the root is. It's just telling you one exists if those conditions are met. Okay, so enough about that. Let's move on now to a test where we can take a look at a polynomial equation and figure out quickly if at least it has a zero at 1 or -1 without doing a lot of work. So it's called the 1 - 1 test. Okay, so the 1 - 1 test, and here's how it works. To check for 1 as a root, so now not only are we checking for 1 as a root, but if we find out 1 as a root, then that also means x - 1 is a factor. So they're the same thing. So we can also use this to find factors. Okay, so what's a test? Very simple. You sum up the coefficients. If they add up to 0, then 1 is a root. How about for minus 1? It's a little bit more difficult, but not too bad. Check minus 1 as a root. And again, what would that be as a factor? It would be x plus 1. So this next test would give us a root of minus 1, or if we want, we could write it as a factor of x plus 1, and we found a factor if the test works. Okay, so for this one, it's basically the same idea, but you have to do something first. You want to change the sign. Of all terms with odd degrees. So go through, change the sign on the odd degree terms, and then do this. Sum the new coefficients. If it equals 0, then minus 1 is a root. All right, so quickly let's see how it works. Here's our polynomial. Okay, so the test for 1 is easy. The coefficients here are 1 plus 3 minus 1 and plus 3. So if I add all these up, 3 plus 1 is 4. Hang on a minute, that's not what I want to do. The test will work there, but it won't show anything interesting. So let me do one thing here. Let's do this. This is better. Okay, so add up the coefficients. 1 plus 3 is 4. 4 minus 1 is 3. 3 minus 3 is 0. So that means 1 is a root, or x minus 1 is a factor. Okay, now let's check for minus 1 as a root. The first thing you have to do is anywhere where you have an odd degree, so that would be here and here. 3 is odd and 1 is odd. You change the sign of the coefficient. Instead of plus 1, that becomes a minus 1. That's an even degree, so we don't do anything. It stays plus 3. That's an odd degree. It's 1. So that minus 1 becomes a plus 1. And then minus 3 is fine because the constant term doesn't enter into the test. You just leave it whatever it is. This time we have 3 minus 1 is 2. 2 plus 1 is 3. 3 minus 3 is 0. So that also means minus 1 is a root. So I just picked up 2 factors. That's a cubic, so I would need to find the third factor. One way to do that would be to either use long division or synthetic division with the 1 or the minus 1 and break it down that way. But we won't go into that right now. So that's how it works. Okay, another way to kind of zero in on possible zeros, but this test is only used on rare occasions, and you'll see why. This one's called the rational zeros test. The reason this one is only used in kind of unique circumstances is, number one, it'll give you a list of possible zeros. They may or may not be. And number two, oftentimes the list is huge. So, for example, if I had, 2 or 3 possible zeros to test, that'd be great. I would just use the synthetic division 2 or 3 times, and I would be able to get going and factor the thing. But as you'll see in this next example, it's going to wind up generating a lot of possibilities, and oftentimes, unless you can eliminate some of them for some reason, there's too many to test. So let's see how it works. What it does is it gives you this number, p over q, it's a fraction, reduced fraction. So it needs to be in simplest forms. These will be possible zeros, and I'll show you how to get p and q in a minute. Again, possible zeros. Okay, so what is p? Okay, p is any factor of the constant term. And we'll see it in an example, and it'll make sense. So, and what is q? Very similar. Q is any factor of the leading term, and remember that leading term, when the thing's in standard order form, will be the left-handmost term, and that should be the term with the highest degree. So what you're doing is looking for the leading term, and then it's going to be factor of the leading coefficient. So the leading coefficient is just the coefficient of the leading term. So an example will make it clear. Okay. Let me see if I can find a good example here. Well, let's start with this one. Okay, this one's not too bad. We'll see how many it leads to. Okay, so for p, what are factors of -3? Well, you got to think of anything that can go in there. 1 can go in there. 1 goes in -3 times. -1 would go in 3 times. And then -3 and 3 are also factors. And then for q, we have factors of 1 are just 1 and -1. So what are the possible p over q's here? So these are all possible zeros. So any of these divided by 1, p over q. So 1 divided by 1 is 1, -1, -3, and 3. And then any of these divided by -1. But I think we'll get some duplicates here. -1, or 1 over -1 is already here. -1 over -1 is already here. And so on. So this one's not bad. So we could test these and find out if any of them divide into here using probably synthetic division would be your best bet. But this isn't typical. Let's look at one more. This is doable, and in fact, we could find out if 1 or minus 1 are factors up here. And then we would only have to test these two to see if they're possibles. So remember, we have the 1 and minus 1 test. Let's look at one more and see how these things can get out of hand. 3x4 minus x squared minus 12. Okay, here's our new polynomial. What we're doing here is we're looking for zeros. Again, we could do the 1 minus 1 test up here and see if those two factors are roots, but we might want to look for others, and this would give us possible factors. And one other thing to notice here, it doesn't really matter what's in the middle. You're only looking at the leading term coefficient and the constant. So the rest of it's irrelevant. As you can see, what's going to happen here is there's a lot of factors for p, and that's going to be the problem. Don't get that p and q confused with p. This is the name of the function. The letter p that we're going to use are factors of the coefficient. Here's the problem. Got plus and minus 1, they're always factors. 2 goes into 12, so we could divide it by a positive or a negative 2. 3 goes into 12. 4 goes into 12. 6 goes into 12. And 12 goes into, whoops, I'll put the 6 here. 6 goes into 12 and 12 divides itself. Here we have plus and minus 1 or plus and minus 3, and that's it. Okay, but look what happens here. P over Q. Look at all the combinations. All of these divided by 1 or minus 1. So plus or minus 1, plus or minus 2. Basically, it's all of these. I'll keep the same order. Then I got to test use plus or minus 3, any p and q. So I got to add to this list. Plus or minus 1/3 could be a root. We don't know. Plus or minus 2/3. Okay. And then 3 goes into 3 once, so that's going to be back to plus or minus 1, so we got that one. Plus or minus 4/3. Three goes into 12 4 times, so already got plus or minus 4. And 3 goes into 6 twice, already got that. But look, each of these is plus or minus, so 2, 4, 6, 8, 10, 12, 14, 16, 18 possible roots to test for. Again, we don't have to test for these using division. We could just use a plus or minus 1, so we might get lucky there. But all of these others, you would have to test for them. So anyways, at the very end of 4.3, I'm going to work a word problem where the rational zeros test does come in a little bit handy. So you'll see a case where it kind of is useful. But generally speaking, it's kind of like the intermediate value theorem. Interesting, but not all that useful. Okay.